On January 10, 1990, the McDonnell Douglas MD-11 made its inaugural flight in Long Beach, California. The flight officially kicked off an ambitious 10-month, 5-aircraft FAA certification program. Following are some of the highlights and results of those certification tests. Actually, flight test activities began long before the first flight. During MD-11 assembly, over 350 miles of flight test wiring was laid and more than 1,000 remote sensors were installed to measure specific temperatures, pressures, accelerations, stresses, and various other sources. In addition, some 90 digital aircraft buses were interrogated for thousands of additional measurements. These buses comprise the heart of the MD-11 computer-controlled engines, automatic flight, flight management, electric, hydraulic, environmental, and fuel control systems. By the time the aircraft were ready to fly, the onboard data acquisition systems were prepared to record nearly 8,000 different measurements per aircraft for real-time in-flight and post-flight data analysis. A flight deck simulator was designed to complement flight testing, check out software, and permit pilot evaluations. The simulator represents the MD-11 cockpit display and is run by actual aircraft computers. Before its first flight, the fully assembled MD-11 was subjected to a series of ground vibration tests to demonstrate that the airframe had sufficient structural damping characteristics when subjected to certain vibrations. Following its first flight out of Long Beach, the MD-11 and its flight test crew moved to the Douglas Aircraft Flight Test Facility in Yuma, Arizona. This would be called home for most of the certification program. Entering the flight phase of testing, the MD-11 first executes a normal takeoff. Including its maiden flight, the first article MD-11 flew 4 consecutive days. This is a first in Douglas aircraft history and demonstrates an unprecedented dispatch capability. The test program proceeds with a series of structural aerodynamic damping tests to systematically define the flutter-free altitude and speed regime at which the structure can safely fly. Externally mounted flutter vanes were used to control pulse frequencies applied to the aircraft control surfaces. Several stall tests were conducted to define the aircraft's minimum in-flight airspeeds and their variation with respect to weight, altitude, and various aircraft configurations. As the buffeting in the airframe communicates a stall warning in these low-speed, high angle of attack regimes, the pilot demonstrates the aircraft's excellent handling qualities through the stall and recovery. All the stall speeds demonstrated by the MD-11 met or exceeded the predicted results. Although the MD-11 does not use thrust reversers in flight, this test was performed to demonstrate that if an inadvertent deployment occurred, the aircraft would still be controllable either through a safe stowing operation or a safe landing. Lateral directional controllability was satisfactorily demonstrated with the #1 engine thrust reverser deployed in flight during a simulated approach and eventual landing. As part of a continuous improvement effort, tufts were installed to identify, through flow visualization, areas of airflow separation that could be addressed for future performance improvements. As a result of this testing, various drag improvement devices were developed. In July, the MD-11 flew into the wake of Hurricane Iselle off the tip of Baja California to perform natural icing tests. The entire test phase was accomplished in an unprecedented single day, during which the aircraft's ice detection and anti-icing systems performed as expected. MD-11 safety and reliability during ground operations are just as important as when the trijet is airborne. Here, the integrity of the anti-skid braking system is tested on a wet runway. In this demonstration, the aircraft exhibits positive braking performance during a landing rollout. Landing performance tests are conducted to determine the air distance measured from a 50-foot altitude to touchdown, and the ground distance measured from touchdown to a full stop. The MD-11 completed over 40 of these demonstrations for FAA certification. Rejected takeoff performance demonstrations, or RTOs, are conducted to determine the distance required to reject the takeoff from the decision speed, or V1, down to a full safe stop. Slow motion, high-speed film captures the operation of the anti-skid system during the run. This demonstration was the most critical of the rejected takeoff test series. The energy of the aircraft at the brakes-on speed was the maximum energy the aircraft is certified to dissipate, over 800 million foot-pounds of energy. McDonnell Douglas was the first in the industry to conduct a 100% energy rejected takeoff with 95% worn brakes. In addition, the aircraft is seen here taxiing clear of the runway on its own power after coming to a complete stop. Because of the extremely high temperatures generated in the wheel, tire, and brake assemblies during the RTO, fuse plugs are built into the wheels. When the fuse plugs melt, they release the air in the tires to prevent them from bursting from the heat and causing injury. Ground minimum controllable airspeed, or VMCG tests, are performed to determine the speed at which the aircraft is safely controllable to continue the takeoff when a critical engine is suddenly made inoperative during the takeoff ground roll. Again, excellent characteristics are demonstrated. Takeoff performance tests are conducted to determine the speeds and distances required to take off in various conditions. After the nominal speeds are determined, the aircraft is subjected to a series of abused takeoff conditions. Here, the aircraft is rotated at a rapid rate, 10 knots below the normal rotation speed. A half-inch thick steel skid plate was installed in the contact area for this series of tests. Automatic go-arounds or missed approaches were performed to verify minimum altitude loss from the go-around initiation to a positive rate of climb, and to ensure adequate airspeed guidance and tracking. Crosswind takeoff and landing tests were conducted at Great Falls, Montana. Here, the MD-11 exhibits excellent controllability and handling characteristics in a 25-knot direct crosswind landing. On November 8, 1990, the MD-11 received initial FAA certification. During the previous 10 months of intensive testing, the MD-11 completed over 1,400 flights, 2,300 flight hours, and more than 1,500 ground test hours. During an around-the-world flight series, the MD-11 covered 22,290 miles in 43 hours and 13 minutes, setting international speed records on each of 3 legs. The MD-11 flew from Dallas, Texas to Seoul, Korea in 14 hours and 49 minutes. Flight time between Seoul and London was 13 hours and 24 minutes. The final leg between the North Pole and Yuma, Arizona took 7 hours and 45 minutes. The tests you have just seen are only a few of the many that were conducted on the MD-11 during its flight test certification program. These tests were very extensive and stringent and verify the essential integrity of this aircraft. The magnitude and complexity of the MD-11 test program required a team effort from all Douglas employees, suppliers, and regulatory agencies. Their combined effort and dedication make the MD-11 the premier passenger jet of the 1990s.